So what we'll move on to speak about here is the ionic basis for how the electrical activity moves through the heart. And so because we have two types of cells in the heart, we have autorhythmic pacemaker cells, and then we have contractile cells. So the ionic activity, what's happening in terms of what ions are moving, sodium, potassium chloride, calcium, what's happening inside the cell that is allowing for the electrical activity, that is going to differ depending on which cell we're looking at. So there's going to be the pacemaker cells, how they spontaneously depolarize. And then we'll look at the contractile cells later on and how they depolarize based upon input that's coming in. So they are not pacemaker cells, the contractile cells. And so they're going to have to receive the electrical input in order to actually contract. All right. So let's start out with the pacemaker cells first. So because they have this autorhythmic ability, they can spontaneously open and close ion channels. And in doing so, they spontaneously fluctuate the membrane potential. Thinking all the way back to Unit 1, when we said that the membrane potential is really a reflection of which ion channels are opened. If I've got sodium channels opened because of the ECDF of sodium, sodium is going to rush in. And so that's going to spontaneously depolarize, right? It's going to start having a positive membrane potential change, which will lead to a depolarizing event. Same thing with potassium. So the spontaneous depolarizing events that we see for these autorhythmic cells is a reflection of opening and closing of these channels spontaneously that results in membrane potential change that results in the action potential being fired. So we start out with sodium potassium channels opening up, right? So we have sodium and potassium channels opening up. This allows for a net movement of sodium into the cell. And so this is where we start depolarizing because of the opening up of sodium channels. Potassium channels are closing at this point, but there are funny channels that are opening up. And the funny channels allow for both sodium and potassium movement, such that the net direction, the net movement is for depolarization to happen. After that initial depolarization, we then see calcium channels open up. So calcium channels open, they're going to further depolarize the membrane potential because calcium also has an inward ECDF. So as that calcium comes into the cell, it's going to spontaneously increase our membrane potential. And then we're going to get to the action potential. Now, there are two types of calcium channels here. And I forgot to write it in at this one, but this is going to be an L-type calcium channel. So an L-type calcium channel is a slow calcium channel, and that's what's going to cause the initial further depolarization from rest. Now, the actual upstroke of the action potential here is going to be caused by T-type calcium channels. These are also referred to as fast calcium channels, and they're going to be responsible for the actual action potential, that upstroke all the way up to positive, and then all the way back down, which is going to be caused by potassium. So that repolarization coming all the way back down is going to be caused when potassium channels open. All right, let's illustrate that here to make a little bit more sense. So here is the ionic movement that's happening inside a pacemaker cell to result in an action potential. We start at about positive, we start at about negative 70 millivolts, so the resting for our pacemaker cell. We then have the closing of potassium channels and the opening of funny channels. And funny channels allow for both sodium and potassium, okay? But they allow for more sodium than potassium. So because potassium channels are closing, funny channels are opening, this is a net inward movement of more sodium than potassium. All right, and so that allows for a positive membrane potential change. In other words, an initial depolarization that's shown here in green. From there, we have a further depolarization. We open up the slow calcium channels, also called the L-type calcium channels, that are shown here in pink, and that kind of just further depolarizes the membrane potential. So there's some more positive change as calcium comes in. During this phase, however, we've now closed the sodium channels that were initially opened. So the pink phase here is representing the opening up of slow calcium channels. So the membrane potential for calcium increases, the membrane permeability, for calcium increases, and we're going to close those sodium channels, those funny channels that were initially open, and the membrane permeability for sodium will decrease. We then have our threshold met. So from there, we have the rapid upstroke, which is shown in orange here, and that is the opening up of fast calcium channels, also called T-type calcium channels, and they are going to rapidly depolarize the membrane potential. So we're going to have a rapid increase in the permeability for calcium. Calcium rushes in and allows for the action potential to occur. So the action potential in pacemaker cells is due to the opening up of fast calcium channels and due to the movement of calcium into the cell. All right. And what I want to make, the connection I want to make here is that we know that calcium is needed for the regulation of muscle contraction. It's going to bind to troponin. It's going to cause tropomyosin to uncover the binding sites. And so that is why calcium is involved in the action potential with these types of cells, because that calcium needs to rush into the cell, bind, regulate that the regulatory proteins on actin, and allow for cross bridges to be made and cross bridge cycling to happen. Whereas when we look at our neurons, we saw that the action potential was owed to from sodium. The rushing of sodium into the cell was what brings about the action potential in neurons. But here in muscle cells, especially pacemaker cells, calcium is the ion that's responsible for the action potential, also for the regulation of muscle contraction as that calcium comes into the cell. Okay, so just representing or illustrating that here in a different way so we can see the membrane potential go from -70. This is where we have that initial depolarization from the funny channels. Then we have even further depolarization from the slow calcium channel. So that's these two spots on the graph here. Then we have the rapid upstroke, which is our fast calcium channels. Then we have repolarization, which is opening up of potassium channels. We know potassium has an ECDF to move out of the cell. And so as all that positive charge leaves the cell, we now see the membrane potential go all the way back down to -70. Okay. Let's contrast that to the ionic basis of the electrical activity in a contractile cell. So a different cell altogether. This is the contractile cell. These are the cells that will receive the input from pacemaker cells and then result in actual muscle contraction. So we've got phase 0, which is where we have an increased permeability to sodium. So sodium channels open up. Phase 1 is where we have a decreased permeability to sodium. So sodium channels close. So phase 1, sodium channels open. Phase 0, sodium channels open. Phase 1, sodium channels close. Phase 2 is where we see an increased permeability to calcium and a decreased permeability to potassium. So during phase 2, we're kind of stalling at this point. We open up calcium channels, we close potassium channels, and we prevent the cell from repolarizing. We want the cell to linger in this depolarized state to allow for more calcium to come in, right? Calcium is also going to be important in regulating here again. But then closing the potassium channels prevents that repolarization from taking place. So phase 2 is really this plateau phase. It's the stalling phase, allowing time for the cell to linger in its depolarized state so calcium can enter. Phase 3, we then have a flip-flopping of the orientation of those two channels. So now potassium channels open, membrane permeability to potassium increases, and calcium channels close, membrane permeability to calcium decreases. So we kind of flip-flop the events of phase 2. And so now we can stop the calcium from coming in, and we can allow for potassium to leave and allow for that cell to repolarize and go all the way back down to phase 4, which is resting membrane potential. Now, the duration of contractile for cardiac muscle cells is longer than skeletal muscle. very similar to what we said for smooth muscle as well, much longer contractions. So skeletal muscle has very quick 1 to 2 millisecond contractions. Cardiac muscle, on the other hand, smooth muscle included, have longer, slower, more sustained contractions. Okay, let's illustrate the event of that contractile cell ionic movement here again. So we're starting slightly more negative. So a contractile cell differs from a pacemaker cell in that we start off with a more negative resting membrane potential. We then open up our sodium channels, which is phase 0 here in blue. Open up sodium channels, membrane permeability for sodium increases, sodium rushes in, which is what gives us the rapid upstroke here. Okay, so this is another area where this differs from the pacemaker cell. So the rapid upstroke of the action potential in pacemaker cells was owed to calcium. The rapid upstroke of the action potential in contractile cells is owed to sodium. All right, sodium rushes in, and then we have phase 1 where sodium channels close. So sodium channels close here in the orange, which is phase 1, and then we get into our plateau phase or our stalling phase, where we have the opening up of calcium channels, but the closing of potassium channels. And so that allows for potassium to not move, so we prevent that repolarization for a bit. This is what allows us to stall here or plateau. But we do allow for calcium to come in. This keeps the cell in this depolarized state, so it keeps the membrane potential really high, really positive, but also allows for that calcium to regulate muscle contraction, to interact with troponin, and to allow for cross-bridge cycling. We then proceed to phase 3, which is where we flip-flop the orientation of those two channels. So now we close calcium channels, the permeability for calcium decreases, and we open potassium channels, the permeability for potassium increases. And because potassium's permeability increases, we now have potassium rushing out of the cell according to its ECDF, allowing for the resting membrane potential to be reestablished. So the membrane potential becomes more negative. This is where we have repolarization of the cell, and we go right back down to phase 4, which is our resting state, all the way at the bottom here, -90. Okay, so similar events being shown here. We start with phase 4, phase 0, phase 1, phase 2 being that plateau or stalling phase, and then phase 3 being repolarization. Okay. Some of the properties that we see that are similar to skeletal muscle are the presence of the T-tubules to allow that impulse to travel quickly, the sarcoplasmic reticulum where that calcium is stored, and then the regulation of muscle contraction with the help of troponin and tropomyosin. So those are all shared properties between skeletal muscle and cardiac muscle. Properties that are shared between smooth muscle and cardiac muscle are gap junctions. So gap junctions are present in single unit and cardiac muscle, as well as the source for calcium for the contraction, for the regulation of the contraction. So in skeletal muscle, it's only coming from the SR. In cardiac and smooth muscle, it's coming from the outside of the cell and also coming from the SR. So there's an additional source of calcium coming from the extracellular environment.